Hello, everyone. In this video, I'm going to give you an explanation about analytical and numerical solution. So analytical solution versus numerical. And of course, this is not that we're going to pick choices and stuff. It means just to understand the connection between uh, these types. And that will help you have a better understanding for the whole thing. And I'm going to use, of course, a simple example because the goal is to understand these concept. Then, of course, as we move on, you will have much, and we did already much challenging examples. So let's see here. You have analytical and you have numerical. And of course, at this point here, we've seen different types. And let's say, of course, ODE1, um, at the beginning, differential equations that are first order, and let's say linear, uh, separable, and let's say exact, for example. Let's say up to this video, you've seen these. And for numerical, let's say same thing, first order, and you've seen a method that is Euler method, and that's an approximation method. So here, the goal, this is kind of like a closed form that gives an exact solution, right? Here you get an approximation solution. So that's kind of you try to use the numerical. Of course, it has its pros, and you're trying to get to that exact solution. So analytical, you may run into a case that it's impossible to even do. It doesn't mean now that it cannot be done. It just means you need to shift to numerical. All right, so let's maybe put this when analytical is impossible, let's say, to do, you're going to shift to numerical, right? Or sometimes you use numerical to figure out where the solution is, and you can explore your ways of finding analytical as well. Okay, so now that we have this kind of understanding, and let's try over an example. And I'll use a simple example here. This first derivative equal y. So as you see, this is kind of course, differential equation. However, kind of like this, which means the right-hand side depends only on y. This will give us a really good feature that makes these kind of functions autonomous. Okay, and I'll explain it when we look at direction field or slope field. So just kind of looking at it. So now let's explore the analytical side. Of course, I need to find what type is this. It may be more than one type. So let's ask, is this linear? Well, if it's linear, then putting it in this form, it should fit that description that we talked about. And yes. That means you can find the integrating factor here, and it's going to be this. All right, let's multiply now the equation by it. Which gives us this product. All right, that means when integrate, you're gonna get the product out and you're gonna get some constant on the right side. And now multiplying by EX or dividing by that factor will give us Y equal to, let's put C first. Even though it doesn't matter, but just for a look. So this gives us kind of the idea uh, about it. And we can explore finding, let's say, an IVP or uh, kind of solve and figure out what is the flow to these solutions. And we can do that. Let's get you the question here. So dy over dx is this first derivative equals to y. Let's give you kind of an idea here. And so it's not 0, x. So if I have x, y, and I have the slope. Let's say I pick a point 0, and I will get 1. And let's change this to IVP. And so we connect it with numerical example. And in this case, using initial condition, you get 1 equals C to this, which means C is 1. So the particular solution is this, okay? And that's what the solutions are expected, kind to give you an idea. So they are exponential curves, but now have to do with C. If C is using this condition, C is 1, you're getting this curve. But C may be -1, right? You get this curve, something that opens down. So you can see here that you have a lot of different curves in this solution, in this general solution. So if I do, I take a point on a plane, let's say 0, 1, and if a solution goes through this point, then what does it mean? I need to calculate the slope. dy over dx, as I mentioned previously, equals to y, so it really just depends on y, so it's going to be 1. So you come to this point, and you're going to do a slope of 1, like go up 1 over 1, something like this. So the autonomous idea here, let's say you go to 1, if this if y-intercept is 1, again you use to find the slope, it'll be 1. So 1.11, right? The slope is 1. So that's kind of what's good with these autonomous property here, that it gives you the idea on this kind of a slope field or direction field. All right, so we can do more question or points. Let's say I pick -1. if I pick -1, if I put 1, it'll be the same thing. So what if I put 0? That means y is 0, the slope is 0. So it'll be here. And same thing. So since now I know this is autonomous, that means every point I would pick, the slope would be something like that. All right, let's pick 0, but this y is -1. Then the slope is -1. It's going to go this way, right? Negative slope. Now, so that gives us an idea on these. All right. So here, this slope field, the more you do of it, the more it gives you how the solution will flow. So for example, if c is 0, right, then y is 0. You can see kind of here what's happening. But if c is 1, you're getting exponential function, so you can get a feel that it's going to go this way as we do more of these small lines, and they're going to fit nicely. So this is kind of a quick idea based on the textbook for us that you see here in the picture. These are in section 1.3, learning how to graph these type of vector fields, and there is method of isoclines and stuff. So we will have a chance to do more on these. But this kind of at least gives you an idea for analytical solution. You come up with the general solution, and the direction field gives you a graph or a plot that will show the flow of solutions. And it will be helpful later because if you're looking for some idea, let's say critical point, then it will be clear to see there. So we will get to that. Okay. So now let's talk about, I did this analytical. Is it separable? Let's see. I'm staying in analytical because I think probably if you haven't seen one that can be done different ways, yeah, let's ask that question. All right, is this separable? All right, so and divide. Yeah, yes, it is. Then we can follow that. Integrate. Right? That's natural log of the absolute value of y, and that's x plus some c there. Take the exponential to both sides. Then we get this, and you've done this a couple of times now. Then we need to get this y out. It's going to be, let's call this c1. So, right, some constant. Then I separate the two. Okay, and we've done this. This is just a constant. And I will factor this in it, right? Arbitrary constant that is positive or negative. So now that's going to be this c to dx. So we got same general solution. It just, you see, different skill maybe is needed for this one. All right, so now that we know how analytical solution work and the profile, we can connect this with numerical. And for numerical, since now you've seen the approximation method of Euler here, we will use that. And I think probably Euler here used it to find the uniqueness and the solution and the existence and the uniqueness of the solution. Then later on with the computers, you're like, oh, this is very handy. Let's see. And there are other numerical methods that are made after that as well. So this use these polygons, you start with some initial condition, right? And use the curve at the points to draw the lines and to keep going toward the solution. And I think it's better just to do this example and maybe use some of the steps. So let's say same thing, we're going to do these IVP, which is this. And we need the initial condition here because we need to start somewhere and start looking for where the solution is. And here to make it simple, we need to find a solution at x equal 1, which means what does this compare to for the analytical? Right? We found y equals c to ex. I did this initial condition and I found y equal ex. So now y at 1 is e, right? So we know the exact answer and we know the value of e. So let's see how this is going to work. And let's decide we will use just 4 steps. Then I'll give the numbers for the other steps we did. So n equal 4, which means h is 1 over 4, which means 0.25. And now you start with this method here, x1 equal x0, which is that, plus h, then y1, y0, which is this, right? And h is 0.25. And f of xn, yn, this is f of xn, yn, and it just means y0, and y0 is, so previous video, of course, we were I went into more details, but that's how kind of you work on this. So 1.25. And of course, you get the idea. This is step 1. Remember, these are 4 steps, so it's not going to keep going forever, just 4 steps. Step 1, then step 2. We will do the same. Just talk about it because we've done it before. X2 is x1 plus h. Y2 is y1 plus h. F of x1, y1. We have y1. We have x1, we have h. So we just put in the formula. So y2 will come up to be 1.5625. y3 will come up to be 1.953. This is step 3. 313, and y4 equals to 2.44141. So you see versus the exact, right? There is some error there. which means if you want to improve the error, improve the method, one way is to increase the n. Let's say we did 16, and that gave us y4, which is of course y at 1, to be 2.63793. So the method, it does converge, which means I got this. Now I increase the steps, I got this, which means I'm getting closer to the exact solution. And I will show you that in there. Of course, you will judge this, and how good or bad depends on two usually ideas. Does the method converge? Here, yes. What is the convergence rate, which you can calculate? And so there are trade-offs in computations, of course. Okay, so what else we need to look at? So another thing is this vector field to show you. And I'm going to use R here, which is an open source, and I will dump in it a code that does this, defines this differential equation, sets up the grid, calculates the slope at a lot of points, and plots them. Let's see. You find it. It's not college algebra. So remember, this is not to go through these details. They are more for understanding the connection. And this is the slope field, but let's look at it. It doesn't look correct, right? So this is the important part that I want to get to, for us to understand that the computer, you can give it, in many cases, will give you output. And if you're designing or analyzing things, that may mean that something is going to break somewhere if it's not correct. But the computer does what you tell it to do. So that's why it's important to understand the background behind everything that we are doing. I see the slope field. You see the red dot there, which is the one we're interested for x equal 1. And look at the slope fields next to it. They're negative, where we expect them to be positive. I also plot the exponential function, the red thing there, that it keeps going up. So I need to fix this, right? All right, clear that out. And now, let's see. All right, so let's compare this to what I was talking about. So now you can see, let's go to that point x equal 1, which you see here as the red. Let's stretch this little more. So you can see that now the flow for the solutions as we are expecting, because C, when it's positive, these exponential functions are growing and going up, and they have this increase in growth. And when it comes to 0, they're flat. Then below 0, they are decaying, but concaving down, which means in kind of slowly. All right. So yeah, so now this matches what we expect. The other, now look at the 2 points. The first point at the bottom is for n equal 4 steps. Then for n equals 16, it's the second one. You see now the point is going toward the red curve, which is the exact solution for the IVP or the particular solution. So this, you can find multiple solutions, multiple curves, and I think this is gives you a good idea about, you can see the analytical solution, you can see the numerical solution, you can also see the computation using a program that will give you the flow field, and from there you can trace. You can also see when you do horizontal line, all the slopes that cross that horizontal line are the same, which makes this autonomous and makes it easy to predict the behavior. And of course, once we see different applications, you see that sometimes tracing these is not too easy. Okay, thank you.